Okay, I want to do a third example of this full vector motion. So we have a kid fires a water gun horizontally from 1.6 meters above the ground, and it hits another kid 2.1 meters away square in the back, 0.93 meters above the ground. What was the water's initial speed? So before we get into this, I encourage you to maybe pause and think about it and get down the relevant information and try to work this one out on your own. So the first pieces of information that we can get immediately come from the fact that he fired the water gun horizontally. So that tells us right off the bat that our initial velocity in the vertical direction was 0. So our initial velocity in the vertical direction was 0 meters per second. We're just going to go through and write down all the information we can, and maybe some of it we won't use, maybe some of it we will. We're just going to get as much as possible. So he fired it horizontally from 1.6 meters above the ground. It hits another kid 2.1 meters away. So it would be tempting to just use this 1.6 meters and say that our initial position in the y direction was 1.6 meters. But this is a problem about projectile motion. The water coming out of the water gun can be thought of as a projectile. And if we want to make use of our projectile trajectory equation, we have to start at the origin. That was how that equation was derived to begin with. So we can kind of manipulate these, and we'll draw a picture in a minute to show how we can make these start at the origin. So my initial position, I want to be 0 meters in x and 0 meters in y. It hits another kid 2.1 meters away, square in the back, 0.93 meters above the ground. So let's go ahead before we get anything else down and draw a picture. So we have our axes here, and we said we want to start at the origin. If we want to use the projectile equation, we have to start at the origin. So this will be the point 0, 0, and this is where we fired the water gun. So fired the water gun, or shot the water gun. Now, we want to put the ground 1.6 meters below this. So we can put the ground down here. It's weird to have the ground not be the origin, but it's just a coordinate. It's just a coordinate. So this is down here at negative 1.6 meters, and we need it this way again to use that equation. Now, the kid that it hits was standing 2.1 meters away. So the water traveled 2.1 meters in the x direction, and that kid was standing 0.93, or it hit him 0.93 meters above the ground. So again, it's tempting to write that the final the final y position was 0.93, but we've changed our coordinate system around a little bit. If it's 0.93 meters above the ground, then we want the coordinates of the ground, which was negative 1.6 meters in the y direction, plus 0.93. And that gives us negative 0.67. So we want to have the final position in the y direction at negative 0.67. So let's go ahead and mark these two things down. So we ended in the x 2.1 meters away, and we ended in the y at negative 0.67 meters relative to the origin. Okay, so now let's get our equation. The trajectory equation was y equals x times tangent of our launch angle minus, and then in the denominator we had 2 times the magnitude of the initial velocity squared times cosine squared of the launch angle, and that was all under gx squared. So let's look at this information. We know where we ended in the x position, it was 2.1. We know where we ended in the y position relative to our origin, it was negative 0.67. It looks like we're missing this angle. So if we launched horizontally, then he just held the water gun straight out in front of him and fired it. So the angle that he fired it at relative to the horizontal was 0 degrees. If he just held it straight out in front of him, the launch angle was 0 degrees. Now, tangent of 0 is just 0. So this entire term just goes to 0. And cosine of 0 is just 1. So cosine squared of 0 is just 1 squared, which is 1. So that term just goes to 1. We don't have to write it either. So we have a pretty significantly simplified expression here of y equals negative gx squared over 2v naught squared. So I'm trying to find, the problem said we wanted the initial speed, so we're trying to solve for that v naught squared. So solving for that, if we multiply both sides by v naught squared, we get y v naught squared equals negative gx squared over 2. And then I want to divide both sides by y. And so I get v naught squared equals negative gx squared over 2. And then to get v naught squared, I want the square root. So v naught equals, we'll just be lazy, it's that all underneath the square root. Oops, I forgot to put my y. We divided by y here, so this should be 2y right there. So all under 2y. Supposed to divide by y. Okay, so you may be saying this doesn't look right. We have a negative underneath our square root, and that can't happen. And you'd be right that we can't have a negative underneath the square root, but remember this projectile trajectory equation started at the origin, and as a consequence of that, our ending position right here was negative 0.67 meters in the y direction. So this y term is also negative, and that negative and this negative are going to cancel each other out and take care of that problem. So now all that we have left to do is plug in our numbers. So v naught equals square root. G is 9.81. That's the acceleration due to gravity. Our x squared, our final position squared, well, we ended 2.1 meters horizontally from where we started. So this should just be 2.1 squared. And then divided by 2 times y. And again, our final position in the y direction was this negative 0.67 meters. Negative 0.67 meters. So if we type all that into a calculator, kind of missed my square root there. If we type that all into a calculator, we get about 5.68. 5.68 meters per second. So he shot the water gun and the water came out of the gun at 5.68 meters a second.